Hello everyone. Thank you very much for giving me this opportunity to share my research. Today is really my pleasure to discuss my works on metallic source-assisted silicon carbon anodes for lithium-ion batteries. Now I'd like to introduce myself first. My name is Huang Shenyang, and I come from the School of Chemical Engineering. My supervisor is Professor Huso Park. In our lab, we will do researches about different kinds of batteries, such as lithium-ion batteries, sodium-ion batteries, zinc batteries, air batteries, and so on. In this introduction, I will mainly focus on my research of silicon-based anodes for lithium-ion batteries. As we know, silicon anode is one of the outstanding examples because of its high capacity, about 4,200 mAh per gram, low operation potential, environmental friendliness, and so on. However, during the cycling, the large volume expansion of silicon will lead to the breakage and smash of silicon particles, making the active substance unable to contact with collector closely, and it will generate the unable solid electrolyte interface, leading to poor electrochemical performances. Researchers have done a lot of works to solve the problems, and the most usual method is using coating materials to build cool shear structure. We can use carbon, metal oxides, morph, graphene, and so on. So our research is mainly focused on to improve the specific capacity retention, ICE, and so on. So the main features is low cost, safety, and convenient methods. And we need to explore the possibility of industrialization of silicon-based anodes. So in this case, I use the one-pot method to fabricate the silicon at silicon oxide at beta bismuth oxide bismuth anodes. We can call it SBG composites. Through this schema, we can find that the SBG anodes were synthesized by 3 steps. First, the bismuth ion intermediate was in situ coated over the silicon by servothermal method. Secondly, the silicon at bismuth ion was loaded on the 2D graphene oxide to build 3D composites. Finally, after the annealing treatment, the bismuth ion intermediate shear would transfer to the bismuth oxide shear and simultaneously oxidize the surface silicon to silicon oxide thin shear, while graphene oxide would transfer to reduced graphene oxide and then oxidize the bismuth back to bismuth oxide. In SEM and TM images, we can find the silicon nanoparticles were well coated by bismuth oxide and flour-like reduced graphene oxide. And in the XRD patterns, XPS spectra and Raman spectra also confirm the existence of bismuth oxide, bismuth, and reduced graphene oxide. In CV curves, we can find the typical peaks of silicon and bismuth oxide, which are linked to the discharge charge profiles. We can find that there are some discharging reactions and charging reactions. In the top right, we can find that the SBG shows an initial discharge capacity of 2746 milliampere-hour per gram at under the current density of 1 ampere per gram and an ICE of 84%. And it displays a great cycle performances with about 1784 milliampere-hour per gram after 200 cycles, which is approximately 700 milliampere-hour per gram higher than the SB anode. The results of EIS test imply that the coating of bismuth oxide and the reduced graphene oxide can truly improve the conductivity. Through the ex situ characterizations for SBG after cycling, we found that the bismuth content was increased while the bismuth oxide content was decreased. This phenomenon is well matched to the results of CV test. So in this system, our contribution is that we enrich the system of silicon-based materials, and we realize the composite of silicon, bismuth oxide, and reduced graphene oxide for the first time, and provided a good guidance for the design of multi-component silicon-based anode system. And it provides ideas for the preparation of next generation anodes. We report a convenient one-port method to fabricate the novel reduced graphene oxide coated silicon at silicon oxide, beta bismuth oxide bismuth anodes, and by two major redox reactions, the beta bismuth oxide is coated on the surface of silicon and the bismuth content is reduced. The above composites show a discharge capacity of about 1784 milliampere-hour per gram after 200 cycles at 1 ampere per gram. So in my future plans, I think the preparation of heterogeneous materials can achieve high electrochemical properties, but it may also lead to the instability of the system. Changing the structure of nanosilicon to about just like the silicon nanowires, the 2D silicon, and so on, and compositing more suitable materials such as metal oxide, two-dimension materials, organic anodes, and so on, may be the breakthrough for next generation lithium-ion batteries. And for the resin coating, the modification with organic or inorganic substance will be an effective strategy to promote the performance of lithium-ion batteries. In some papers, they will add some metal salts or some organic reagent to make the resin become more stable. So that is a good way to increase the performance of lithium-ion batteries. So that's all my presentation. Thank you.